All right, looks like we've got about 33 people in here, so people can trickle in, but we'll just get started. Welcome everybody to the our first SEI presentation for this season. It's going to be a great one. It's an inspection and testing access for the T1 steel. So welcome. Just a couple of things, just so everybody knows, this meeting is being recorded. It has already started recording. Your microphone and camera has been disabled since this is a town hall. And there is, if you look in your top of your teams, there is that QA button up there. So if you have any questions during the presentation, feel free to go in, ask your question. And at the end of Jen's presentation, I will ask her the questions. So feel free to use that function for any questions you have. As for SEI Philadelphia, if you want to stay up to date with us, I encourage you to do so. Our website is sei-philly.org. We have the good information on there. You can always email us at phillysei@gmail.com. And that QR code right there is to our LinkedIn page. That is actually a really good source for information of upcoming events, all the things happening SEI Philly. We encourage you to scan the QR code, follow us, and get all the information. I'll keep it up there for another second while you get your phones out. We look forward to having you all follow us. All right. So for the board this year, we transitioned. My name's Michael Urban. I'll be the chair this year. Colin Drager is our vice chair. Greg Dunn will be serving as the treasurer. Alex Manzi is our secretary. Nathan Dubbs, our program director, so he's in charge of getting all these great presentations out to you. Justin Banks, the director of public relations, and our newest board member, Kylie White. Welcome, Kylie. She's deputy director of public relations, and she'll be working with Justin full-time, making sure he does everything to make sure you guys get all the information via the website, emails, LinkedIn accounts. So definitely those two are the engine for SEI. So definitely great to have her on board. And our past chair, Keith Merle, left us with a good group. So looking to continue. A lot on my plate to make sure keep giving you guys everything that SEI offers. So everybody, welcome. And also, thank you. Last May, we had our SEI Philly golf outing. We were able to raise, I believe, over $4,000, which went to our scholarship. And along with you and our sponsors, Michael Baker, HNTB, AECOM, BDI, Pannoni, Keller, Morshea Bridge, HDR, and SAI. So with those sponsorships and if you were on this call and you participated last year, thank you. The students were, this helps them. That's why we're here. We want to help the students. It's how we got here. I'm sure all of you have received help at some point along the way. So it's great to, give these students help. So again, we're going to continue. So save the date in May, probably early May. We're just ironing out the details of next year. We'll have our golf outing again. So it's a great time. Even if you don't golf, nobody cares. Nobody's good at golf. That's why we're all engineers. So come on out, have a good time. Food, drinks, laughs. Watching me slice the ball 300 yards to the right is always fun as well. So I hope to see everybody there. As far as upcoming events, our next event is going to be our SEI Fall Social. It's going to be at Workhorse Brewing in King of Prussia. This year, we will have murder mystery trivia, so everybody get excited. Last year was, I think it was WWE or wrestling trivia, and for a bunch of structural engineers, I think we held our own. So it was good to see, and let's see how we do with murder mystery. So please, I'll have a next slide for that to sign up. We are working on our October and November events. They'll be they're to be determined, but I'm sure they will be great. And we are always interested in your projects or anything that you're passionate about in structural engineering. So again, if you have any topics that you would like to present to us, reach out and we'll get you on the agenda. As I mentioned, our fall social will be October 14th. There's the QR code. Please break out your phones, scan that, and you can register. It's $25. That includes small bites, 2 drink tickets, and of course this murder mystery trivia. So it's a good time. We had a great time last year. Plenty of food. Workhorse has great beers, along with some other. I think they also have other drinks as well. So great time. The trivia does start at 6:30, so get there a little bit early, grab a table, and we'll have a section cornered off there. So just look for us and come hang out, socialize, and it'll be a great time. So moving on to business, we have a great presentation today. Jen Lanning is our speaker. She'll be talking, like I said, about the inspection of the T1 steel. But about Jen, she is actually GFT's National Bridge Inspection Practice Leader. She has 33 years experience in inspection and quality management, and she's the NBIS Program Manager and manages a large-scale bridge inspection and management projects for multiple agencies, local, state, federal, across the country. She has her BS at Rutgers and an MS from Drexel. Go Drexel. And she is a professional engineer in 15 states. And I might put her on the spot and have her name all 15 states in 20 seconds. We'll see if she can do that. But I will hand that over to Jen. I appreciate everybody's attention. And Jen, I will hand it over to you. And thanks again for presenting to us.
I'm really happy to be here. I'm going to share my screen now, so you have to tell me if you see the screen.
Give me 1 second. I just have to turn it.
Oh, I think I have to put, yeah, there we go.
I got it. I think I got you.
Got it. Okay. Yeah, and I'm not going to name all 15 because I think it's like 16 now. So like, I don't even know. And just suffice it to say, it's a lot. I'm not even the one with the most here at GFT, but I'm catching up. So thanks for having me here. This is a presentation that I've also given as part of a TRB panel earlier this year to talk about T1 steel and non-destructive testing. And it's just a combination of things that kind of created a really interesting project. Technically, it's a little bit outside of bridge inspection per se, but I think it offers a really good look into how inspection is integrated into overall projects, bridge preservation, and kind of response to national emergencies. So just to start out, here's a few details about the bridge. But before I get into that, I'm not really sure like how many people are familiar with the T1 or basically grade 100 steel and the issues that are related to that. If anyone remembers, during COVID, there was the Hernando de Soto Bridge down in Tennessee and Arkansas that had some severe problems, some cracking, and essentially that bridge kind of brought to light a problem that had existed prior to that at the Sherman-Minton Bridge, which is up, I believe, in I want to say Iowa or in that area. But essentially, the use of grade 100 steel has presented a challenge because the era in which it was highly used was also an era that we didn't have D15 testing for welds after fabrication as a mandate. So there's a lot of questions about the overall quality of welds in that time frame, which was the 70s, the use of T1 steel, and then also the way that T1 steel behaves when it's welded. And because of the use of it and the construction of bridges of a particular length and size, there is a common weld detail that required butt weld splicing or basically CJP joints in members that are under tension. So that's really where we kind of start the story. There was a Federal Highways Memorandum after the first issue with Sherman-Minton, which I believe was in 2011 or so, and it said, everybody who has these type of bridges with this type of steel, we need you to go and know which ones they are and check them over and make sure that you have information on the steel and on the bridge and on the fabrication. And then after Hernando de Soto, then a second memorandum came out from Federal Highways that said, oh, no, now because we've had a problem twice with cracking and some failures, we want you to go out and examine, assess, and address all the welds if you can't otherwise prove that you have fabrication testing, post-fabrication testing for these bridges. So a lot of states, immediately said, oh, here's the files, we've got what we got, we're good. Then there was a bunch of structures that they didn't have fabrication files. In the case of the Commodore Barry Bridge, the DRPA did have the files, but they were damaged and lost in a flood at the fabrication plant. And so therefore they could not, prove that they had post fabrication tested these welds. So that's the really, the way the story starts for this particular bridge. I think there were a number of bridges across the United States, on the order of, maybe 20 or 40 or so that had this issue, and the states were expected by March 31st, 2024, to have comply with the memorandum by testing all the welds. So that's the opening saga of the saga here. So Commodore Barry Bridge, owned by the DRPA. It reports to Federal Highways through New Jersey DOT. It's the only bridge in the state of New Jersey that had this type of configuration, this type of issue, which is these type of welds, CJP welds in T100, or grade 100 steel in tension members. So it was a little bit of a high priority, and we still are continuing until we finish some of the work I'm going to talk about, reporting to Federal Highways and New Jersey DOT on a monthly basis as to what a resolution, on behalf of DRPA is happening. So I'm expecting that most everybody on this call is familiar with this structure. It's a cantilever truss. It's over the Delaware River, from Chester to Bridgeport. It's a shore route. Basically, it carries 5 lanes of 322. The ADT is around 35,000 cars a day, probably not the highest that this type of bridge with these issues has seen. The Hernando de Soto, I think, was closer to 100,000 cars a day and a major route, but that doesn't mean that it's not important in any regard. The total length is 13,000 feet, 13.9. And the construction, as you can see, it's right in that sweet spot, 1969 to 74. And the bridge has, it's an interesting structure. I'll show you a graphic in the next couple of slides, but it is really probably the biggest bridge in the country that has had this particular, I want to say issue because that doesn't sound good, but this particular situation. So the type of connections were shop welded and field bolted, and according to what we're talking about, the shop welds were what really presented the questions. So the scope of our project was, and we pursued and won the project in 2022, late 2022, and started work in 2023. And there was several components: perform a visual inspection of the truss, not replacing the biennial bridge inspection, confirming the number of welds in the tension members. Then we were going to perform weld testing because they didn't really have a solid understanding of how many welds there are. And when you look at the shop drawings for this bridge, that's not a failing on the part of the owner or the part of inspectors. There just is not, things are not always built the way, that the drawings say. So that was why we had to confirm the numbers and not make any assumptions. We did weld testing on the T1 welds, and then the owner of the bridge also asked us to do some additional testing on some other welds on the bridge that they had been monitoring for over time, and some members and some different strength things. So we had worked with a couple of other firms to do that as part of our project. And then we prepared a preliminary design recommendations report. And then this did morph into a construction project, as I'll explain. At the time, we were doing quarterly reporting, and we were working with the ongoing biennial inspection consultant on giving them our rating on the bridge, our condition rating. And so going back to my personal experience, this is something where it's a kind of a synergy between design, rehabilitation, inspection, and some sort of evaluation. So my particular experience really lends itself to the inspection and the logistics that are associated with that for a bridge of this size. But then, I would have to say, just as a personal note, and, take this for what it is, 33 years in, I'm still learning. I learned a lot on this project and had the opportunity to really grow my experience and try new things and stretch. So, never think that things are boring. There's always something new to learn for sure. So we had a team that was pretty big, but I think the top two firms that really lend us the most credibility to our project team was Wisjani and the folks there, and Frank Russo. Frank Russo Structural Services. Probably a lot of you folks have either been taught by Frank or know him personally. I'm very fortunate to be a friend of his, and learned a lot from him, and then the folks at Wisjani. And the reason why we wanted these folks on our team is, as you can see, they've worked on a ton in the red of bridges that have very similar. Frank in specific was a key player on the Hernando de Soto. He was also involved in Sherman Minton, and so was Wisjani. Their folks, Travis Green and Curtis Schroeder and Bob Gessel, really were instrumental in kind of starting to recognize the issues around the particular chemical composition of the welded member that creates the issue around what was the problem with T1 steel, right? Like this essentially hydrogen cracking or hydrogen indications resulting from how the welds were worked in grade 100 steel and that chemical composition. We don't have 27 hours to talk about that, so I'll kind of leave it there and invite you to look it up and look for more information about it. But I learned a lot about welding that I did not know, and this is really why this team was key to the success on this project. So we also had other firms. BDI was instrumental in this. We had a ton of testing companies. I knew when we designed the schedule that testing was going to be the critical path. So we really engaged everybody who could provide us with testers, and I'll talk about that in a minute. Wisjani did some forensic analysis, and we had TY Lin on board to perform some design the retrofit. And then, like I said, this whole team kind of then shifted into construction as we got to the end of the design and evaluation portion. So just for like a point of fact here, you can see at the bottom of this slide, here's the Hernando de Soto, right? 1,800 linear feet, about 990 feet high. And then you look at the Commodore Barry, and the main truss is 3,200 feet long, so pretty much double, and was 240, so 50 feet taller than the Hernando de Soto. Doesn't diminish the role of Hernando de Soto in our collective bridge history. I think anybody who does inspection, we kind of get that like story, right, of how bridge inspection came about, how it's grown over time and morphed and changed to. I always tell people every time something falls down or there's damage to something, it changes what we do and how we do our job in bridge inspection. And this is very similar. Commodore Barry has a role in it, but Hernando de Soto really was the catalyst to creating this memorandum that resulted in us having to do the work. Again, Commodore Barry is probably the biggest bridge in the country that has had this issue, though, and you can see just the height alone really lends itself to a lot of my conversation about access, because if I could draw a parallel line to the deck across that structure, you would see, I don't know if you can see my mouse, but right, we had about 180-foot line that was a dashed line on our plan. You'll see it in some of the later slides. That was our equipment access limits, right? We could not go beyond that, and we had to employ other methods. So really, with like a man lift or anything, we had to use something else. So that's part of the story. So I think it's really interesting to have that right here in our backyard here in the Philadelphia area. So we had to do a lot with NDT methods. Again, took a lot of, we did a lot of research, a lot of conversation with folks at, at WJE, Wisjani, to kind of have the discussion about what's the best thing to do, what's the removal of paint, all these arguments that are ongoing and still continue. But what we landed on at the end of the day was eddy current testing. And I go back to the map where we show all the places, at the time we were Trans Systems, we're GFT now, but Trans Systems was also currently working on a project in Texas and doing this work as well. So again, with our combined experience, but down there they used a different type of testing to check for the weld. So we really, they used phased array. So there was a whole conversation around like what was the most cost effective, what was the most, I think implementable in the conditions that we were going to be working. And we landed on shear wave, realizing that, POW wasn't really going to get us that much more information than what we had. We used eddy current to locate the welds, and I have some pictures with that. Shear wave to find the weld. We did remove the paint. You'll see in some of the pictures. We did mag particle after we took out cores and removed the defects where we could. And then we did metallurgical evaluation of the cores, and that was a little bit more destructive. We ended up, slicing them and looking at them under high resolution magnification. So, but as we were putting this project together, we had critical path items, and those critical path items really primarily were the number and availability of inspectors. I've done this job for a really long time, and we all know that there's certain specialties that are hard to get out in the field. One of those is NDT people, and having them on site. So we utilize several firms to provide us with NDT people, but one of the things that DRPA did a great job at was putting in the scope of work, that they wanted to have an established certification or kind of, qualification program in place to make sure that the inspectors knew what they were doing and that they could find these particular indications, because indications that are typical of the type of problems that we were having were extremely small and very hard to find. As noted through Sherman Minton and then Herman DeSoto. So we didn't want to just have people out there that didn't, they might be very good testers, but maybe didn't know exactly how to find what we were talking about, and then be all like, sure, everything's great, move on to the next member. So we had essentially a qualifications period with sent testers to Wisjani's lab in Northbrook, Illinois, and they basically tested them. Curtis Schroeder, who really pioneered the process, tested them on actual members from those bridges to see if they could find it, talked about calibration and set the stage. But then with Wisjani, what they did also is that they provided QA/QC with an independent person every 2 weeks through the whole project of the evaluation portion. And they just came out and they picked, several welds, and they spent a good period of time confirming what they saw on the bridge and what was documented in our documentation. So we had extremely good correlation. There was only maybe 2 or 3 places, and out of almost 1,000 welds, I think that's pretty darn good, where there was some conversation about whether the weld was actually, had an indication or not. But I would say 95 to 97% correlation and good quality control. So we discussed coating removal and decided that we would remove it. There was an ongoing debate, I think it still exists, about whether you can do it through the coating or not. We did remove the coatings at the welds, and then tracking and testing of resolution defects. And I'm telling you, we're still working on construction today. I am 100% glad that we utilized the system that we did, that I'll show you, because we still go back and look and see what was going on there. The level of detail that you had to have to track over 1,000 welds and what was going on with them at any given point and all the moving parts has been really important to be able to have a good system in place. So again, the significant decision points were coatings and then the use of UT versus PAL, and we went with UT. So our weld inspection project, we had a lot of challenges. We performed testing from August 2023 through March of 2024. We had lane closure schedules. We had to coordinate with operations. They might want to do some deck repairs. They might want to do some inspections, some repairs to the lighting, in the gantries, or the bridge inspection team might need to be out there. That was from HNTB. And from AECOM at the time, it was overlapped. And I'm really proud to say I think we really managed that well. We got to know the guys at Bridge Ops and worked really closely with them. They also, would lay down the traffic control for us. And so you had to be aware of when they wanted to pull in the extra lane, the bump out, when they couldn't, what holidays. weather was an issue. I mean, we went from August 2023 through the winter of 23 to 24, and I'm telling you, that was a nightmare. It happened to be probably one of the worst winters we'd had in a long time in terms of wind and snow. And, you know, just because it snows like that day doesn't mean that's the only day you lose, because you have to come off the bridge maybe the day before so they can salt and get the bridge ready, you know, because we could leave our closure up and our equipment on the bridge. Man lifts are not fast moving vehicles. And then coming back on the bridge might take 2 or 3 days. So we would lose a significant amount of time. The cold temperature slows equipment down. So that's also some factors. And then, you know, there were some events and holidays that kind of impacted us. You know, Lionel Messi was playing at the Union and they asked us to come off the bridge, and that caused a whole thing. So we had some, you know, schedule challenges around cleaning the steel and making sure we had a wide enough swath on the bridge. Equipment limitations, as I already touched on, after a certain height on the bridge, we couldn't use man lifts. We had to switch over into utilizing like spider buckets, which some of our testers were not happy about, not at all. And we then had a smaller cadre of testers involved. At that point, the bridge is a very lively bridge, and that also factored into the tester comfort level. At the end of the day, I think some lessons learned that I personally had was I would have probably, because we had a contractor that was a subconsultant to us, and I probably would have been smarter about making them move up some of the use of the spider. Like they left that towards the end, and then it became the critical path, because there wasn't, that those are very slow to move, and then you're standing there. So if we had had other alternatives to kind of like, oh, you move this and I'll go over here and I'll use the man lift, that probably would have been better. So chalk that up to lessons learned at the end of the day. But we did complete testing by March 31st, 2024, and we met the federal highway deadline for the evaluation of the welds. So going back to our plan, started in June 2023, we did a visual inspection of the whole bridge on the tension members where these welds were, primarily just to make sure that there weren't any cracks or any surface breaking indications at the vicinity of the welds. But then we also marked out the welds for the contractor. So you can see here, we're using eddy current to identify. We have plans that tell us the welds approximately here, and then we utilize eddy current to find the weld, because the contractor was going to have to come back and start to clean it. We did some imagery with UAS just to kind of get an overall look at the bridge as well. And then we just wanted to kind of get a familiarity with the structure so that when we were ready to get the testing and coring, we could work with the contractor on that. So then, you know, also during the visual inspection, we were doing utilizing snoopers for the bottom cords, and we had rope access guys, teams out there to do the upper level, again, to do eddy current, because the welds are located on all faces of the boxes. And if you could see from like this picture, he really couldn't go down the side. Those boxes are super deep, and we didn't, you know, it's a safety issue. So we really had to utilize man lifts or like rope access to do the vertical and the underside faces and locate the welds there, because sometimes they weren't all lined up in the same place. You can see here that there's no external, at least on the cords, on some of the top and bottom cords, the transition may be from a thicker plate to a thinner plate, which is where that CJP weld typically happens for this type of structure, is inside. So you can't see anything that lets you know that there's a weld there, right? It looks perfectly flat because the change in thickness is on the inside. You'll see in some of our other pictures that on the verticals and some of the diagonals, the transitions on the outside. And so you kind of get an idea, you know, where you're at. But for these, this is why we had to use the eddy current. So we used a bridge elevation and tracking. Here's an elevation from our weld tracking program, right? Essentially, this is with Janney's proprietary product. It's called Planetate. And essentially, everybody who was on the bridge had an iPad, and this was loaded into the iPad. So all the testers had an iPad with their partner. We provided a team leader for all of them throughout the whole project. And every single weld is located on here. HNTB was from something they had put together. We were grateful for the sharing of information, through the client. And essentially, we located every single weld, and then essentially, indicated where it was. Is it there? There were some that weren't there, that said they were there and they weren't there because of the construction that changes and things on the as-built. Because as you can imagine, these drawings are pretty old. So, and then we had additional, like I said, welds in other places. There were A36 and A588 that had been added into the project as well, which basically came up to over 1,000 welds. So you can see here, this was loaded in, and then we had the screen. You can see the list of all the welds at each place, right? So it had top, bottom, inboard, and outboard. Sometimes there was just inboard and outboard, or sometimes just top and bottom. And then on the side, we basically were able to click out to a Google form where essentially it did the calculation for us as to whether it was an indication that was rejectable or recordable. We put in information, but you can see here too, like the status. There's little dots. You can't really see it on this screen, but the dots were either green, red, yellow. Was the paint removed here? But that's it. Was the test done? Does it need someone to go back? Was a QA done? Do we need to do something with it? Is it rejectable? And so that really ruled our life, right? Like these little dots, and we could print that out. And then also we had pictures associated with it everywhere. So I give 100% credit to Planetate for keeping this job on track, because I can't imagine what we probably would have had spreadsheets everywhere. Here's a little bit about our inspector screening qualifications. We did this testing in July and August, and then we did a couple extra ones as we added some people later on in the process. I was really glad we did this. We sent 9 people, a total of 10 people up there over the course of it. Only one person didn't pass. Everybody else passed. And it really gave us, like I said, this incredible depth of teamwork to be able to shift people in and out. Like I said, that was one of the things I kind of knew. I was like, I don't want, 3 months in this project, so-and-so is getting moved to another job, or he's going on vacation. We had people to back other people up. So it worked out really great. And then a little bit about the quality assurance. But you can see here, this is the kind of things that they were testing themselves on, conversations about, calibration and all of those things. They spent it's like 2 days at the lab, so that was built into the project. So here's one of the pictures where you can see the transition of the weld from one direction to the other. The thickness on that vertical on the left picture. Here's where the contractor went out ahead of us and started cleaning all the locations. This was in some places lead paint, so we definitely had to perform lead protocols and contain our area. Then you can see on the right picture where there's like a little bit of a spray paint mark. That was what they did when they did the previous thing. They had the eddy current, and then they spray painted it down the side, so at least the contractor knew where they were going and what they were doing. And then the different access methods, varied, right? Maintenance walkways, walk-in top court, underbridge vehicle, bucket truck and man lifts, spider baskets, and rope access, all to get up there. We even had to find a tester who was rope access certified in order to get that work done on the structure. Here's some more pictures. I know pictures are worth 1,000 words. So there's the spider basket, and this is a beautiful day for the spider basket there. And you can see the man lifts in there too. So we're working with 2 pieces of equipment at the same time in a similar area on some, very tight connections. You got to really think about like the overall, density of the bridge and all the the lateral and the portal bracings that were in place here that really created a challenge sometimes for getting equipment up and down. The pictures in the middle are the top one is, again, the spider basket where we took the wings off to make it move quicker. It wasn't as heavy, but moving these from place to place was what really took the time. And they don't go very fast either. So that was why I think, in retrospect, we should have kind of put them a little earlier in the process. But, hindsight's 2020, and I'll know better next time if this ever happens again. And then you can see down here, the tester in the bottom picture is working on underneath the deck in, standing on a gusset plate where he's tied off. So then original contract scope required taking 10 core samples, utilizing those to do some metallurgical analysis, try and determine what the nature of the indications that we were finding were, and is there a propensity for the hydrogen type cracking on this bridge. And we had 5 by the end of 2023. Some of them were actually remediating core testing that had been done earlier in 2012 through 2022. The DRPA was including testing of some percentages of these welds as part of the biennial inspections, and that was then derailed with the whole must do this now from Federal Highways. So they were in a process of kind of testing as they went until that mandate came out. So we went and took 5 of the cores right away. And then in February 2024, kind of simultaneous with the finishing up of the testing, we just started coring locations that we knew were really contained small rejectable indications, because that was really what the resolution was going to be anyway, to remediate the bridge. Federal Highways wanted these addressed. They considered them critical findings. And so New Jersey's like, that's an emergency and you need to get rid of them. You can't just now walk away from the bridge and go this location, that location. So we started down the path of remediating within the first phase of the contract. And with Jenny, like I said, did some of those cores, and then we had the contractor trained to do the cores. And you can see it's a pretty big piece of equipment. It's a mag drill and requires a lot of effort. We have to tie it off, chain it off, and then we really wanted to retain the core, so that required a little bit of modification to the piece of equipment, the drill, so that we didn't have the piece go thunk into the bottom of this giant 5 or 6 foot box and then never to be seen again. That was really important to us so that we could retain them. We had all of the cores, which totaled maybe over 100 from the project. We typically used either a 3 inch or a 1.5 inch core to get rid of it. And then if it wasn't fitting in that, we did a different resolution as we went through the end of the project. We had all of them, and Federal Highways recently picked them up, and they're going to keep them and some of the other ones, the 3 inch ones, and some of the other ones from other projects across the country to do some kind of research or maintain them for future research. So we're glad to have contributed to that as well. So at the end of the day, the status was that there was previously 143 welds under the biennial testing program. We retested 12 of those because we were unsure of the consensus on those. And then we did 594 welds that were the A514 steel and the grade 100 steel. And then and then we had additional probably close to 500 welds for the A36 and A58, which were kind of a different project concept over there, checking for some strength issues in those members. So, but we reported to Federal Highways only on the A514s, and as you can see here, we had about a 15% rejection rate, which was really interesting at the end of the day. And then we did have 18 inaccessible welds. Those are welds that are really sitting at a kind of a confluence of multiple weld locations up in the top at a, probably a 5-member connection point in a few places. And the weld testing there would be inconclusive due to the overlap situation. So they're just going to have to be visually inspected on a regular basis. But that's the results of what we had going on. And the reason why they're uneven is because some of the welds in that 143 were tested more on one truss versus the other truss. So our testing conclusion is that many indications were found that wouldn't pass today's D15 inspection standards. Not all were crack-like indications. Most of them, as a result of our coring, really were junk in the weld, just unclean, didn't scrub, stuff from the stick, just not a main main problem, right? Just kind of like welding at the time in the 70s when that was done. We indicate that probably similar rejectable indications exist in many of the non-T1 welds throughout the structure, because those don't have a recorded history of these kinds of failures and problems that were typical of Hernando de Soto and Sherman Minton. Then we're just going to live with it and go forward until such is different. So, it just is what it is. Plan of critical action we had to do to get the remediation to be complete by September 2025. We are mostly on track with that. They've started another painting and repair job that's going to finish up the last couple of locations this month. We started an emergency remediation contract to address the additional cores that we didn't get, or the ones that were bigger than that. And that led us into coring and plating solutions that I'm going to talk about in a second. And then we had a preliminary design report. We did a draft of that report. We turned it in December 2024 on time, got comments back, but we paused it because at that point we were so deep into the repair project that I think what we're going to do is wait until the repairs are done and then basically create a scope of the whole project, so that we're not only reporting on part of it and leaving things undone. We're just going to give them everything we did and put a period at the end of the sentence. So the emergency remediation contract consisted of the following: coring, and it went to the contractor that was working with us, although they separated out from us, to now work independently as a contractor, primarily just because, a lot of consultants aren't insured to do construction work of this nature. So we, though, stayed in place as the resident engineer and the construction manager. We had coring locations of like 1.5 and 3-inch cores at 54 locations. We did intermediate repairs, which they're kind of like a little bit of a Franken repair. Like they would have maybe multiple cores, look like a snowman. Some people call them a dog bone or a slot. Just some of them are located like at the corner of a box. So we had to be a little creative with how we remediated those. And so is there a detail for those? No, it was on the fly. We came up with a solution. And then we had about 42 total plating repairs that were, preliminarily designed kind of by like a space of this is this connection, this is what a plating repair would look like. But each one was designed individually in the shop drawing phase, like field verification shop drawing, because the configuration of that connection might be a little bit different, or existing bolts and that kind of thing. We did a structural analysis to evaluate the member capacity with a reduced section. That also determined whether something became a plate or stayed a core. There were some welds that had, rang the bell for like half of the weld or the whole weld, and those went immediately into the plate pile. We didn't really play around with that too much. So then we reconfirmed all the locations prior to coring. So we had the tester come back out, reconfirm it, and then they magged the interior of the hole. A couple of them ended up where we had to drill a second hole, or when we went to drill again or buff out like maybe like a mag particle indication that didn't say we were clean, we ended up having to throw it to plating because we just had a really junky location and couldn't resolve it with a core in a way that would maintain the member capacity. So on the fly, making decisions, I think that's part of bridge engineering in a lot of ways. Not everything is always cut and dried and beautiful. You have to just go with the flow and figure it out. We had to, again, maintain the access. We had to put in long-term wide load restrictions in place. We had challenges to get people at height for extended periods, because now it just wasn't go up, test, come down. You had to stay up there, put in plates, work within box members. We had weather issues. As you can see here, this is what they call the shark cage, or it's essentially an enclosed repair around the plating location. And then we also had to provide a horizontal safety line across the top cord to tie off the workers, because you have multiple people up there now working up there for extended periods of time. So we had to do these, the crane pick plans and that kind of thing. So you can see here's some of the inside of these boxes that protect both the worker and the traveling public. Didn't want to drop tools or drop a bolt, and let folks work up there relatively, I say relatively because it's probably not fun on a given day, but relatively safely from and protected from the weather. I mean, everyone was safe 100%, but the weather was a real challenge in these locations. So we had these work platforms up there. You can see here, we still went back to the coring. You see the notes for the weld number and name and picture. And then I don't think I have a picture of, maybe I do. We used plumber's plugs for the welds to protect, or for the cores to put them in there and prevent weather from getting in there, moisture and animals, birds and such. So we did that. Here's some of the pictures of the plating work. You can see drift pins in the middle picture on the bottom. You can see some holes are pre-drilled, and then they come up and field drill the remainder holes to get the plates on. In the places that there is existing bolts, you have what's called a cheese plate in place. Really was a creative amount of effort. T.Y. Lin did a fantastic job reviewing shop drawings and advising the contractor and approving the work plans. You can see here's some places where we had multiple, there's the plumber's plugs on the picture on the left, where we had to do some creative coring and resolve these. And you can see the note here, MTOK, just knowing that we cleaned up and got rid of the items. So at the end of the day, I think I've talked a little bit through the whole talk about lessons learned, but I think the big points to take away from here, this is probably not like, look, bridge engineering is like a very dynamic, living problem. If we ever have to be in this situation again, takeaways are inspector qualifications are super important. If you don't have good information coming in, you don't get good information coming out. Our QA for NDET, we had thought about that at length and really made the point in our presentation to win the work that we knew we'd need to do that. Really take account of things that affect production rate. I learned a lot, like I said, on what I would do a little differently if I had to do it again. And then the testing and management tracking application, investing in that, bringing that to the table, I think was also one of the decision points for the client, for the bridge owner to choose us, because we had put thought and effort into it ahead of time when, we weren't just going to be using paper and spreadsheets. We were being innovative and going from there. So we're talking now. So done talking, questions from the group, but thank you.
Thank you, Jen. That was great. Everybody, you can use the QA function if you see it at the top of the Teams. It's don't use the chat function. Use the Q&A if that's up there. So we do have one question. We have a question here and a follow-up, I guess. What grades of steel were used on the project? And I guess it's the steel for the existing and then any repairs.
Oh, Ed Montgomery knows the answer to this because it's Ed Montgomery's project. Ed sneaking in here. It's a good question. It's actually a really great question. So when the design was initially put together, we had, like I said, T.Y. Lin did very generic designs for in case we found something during the course of the project, and that was under a separate task. And initially they did the design work utilizing grade 100 steel, which at the end of the day was not the best choice because it's hard to get. It's not often run and doesn't really sit around at steel mills. So we collectively with Frank Russo and our team went back and said, hey, we think you should do this for grade 70 steel at a minimum so that, we're not dealing with giant thick plates, but also something that's more commercially available and more readily able to be purchased. And so the grade of steel that was used for the repairs was grade 70 steel for, I think, 99% of the repair work on the project. So. Nice to see you, Ed. I know you can't respond, but yeah. Ed Montgomery was the project manager at the beginning of the project, and we were sad to see him retire at the beginning or the end of last year, and he hasn't been with us for the rest of the project, but he really was a great client to work with, and we miss him a lot.
If anybody has any more questions, I actually have a couple, so
sure, go right ahead.
I'll ask one. So I guess more as as the the PM and everything on this, how many? It's kind of two-part. How many crews did you have at once? And then I guess when you're putting a proposal together like this, how, from what you I guess put together as in the proposal stage, and then what you were able to actually implement in the field, how did that work out?
I think we were pretty well on target with the field teams. We crashed the visual inspection with probably several teams at a time. But because of the structure, the way it is, you can't there's a limited amount of stuff you can do. You can't be on both trusses at the same time. It's just impossible because there's 5 lanes. You're going to be in the 3-lane side. You're forcing the bridge to be at 2 lanes on the other direction. Nobody loves that. The public hates you. There's a whole lot, but you can't really mobilize and work on both trusses at the same time. So I think that really affected, a lot of what we did. I think we made the right choices in the amount of teams that we had doing the visual inspection. We ran 3 testing crews at a time for most of the testing work. And I think that was really on point. That was about the max that you could do and not, have your equipment running into other people's equipment and interfering and all that kind of thing. I think I would, in like I said a couple times, I would do things a little differently with just the scheduling of getting like those spider baskets out there sooner. They were on site, but the contractor, didn't really want to use them, and I don't blame them because they were kind of paid. But they, I think we probably would have pushed a little harder. Because they went out and did steel cleaning ahead of us, and then we came out and started testing, and then they were still steel cleaning. So they were in like maybe 2 or 3 other locations while we were testing in 3 locations. So there was a lot of activity, and I think we were on point with most of it. I do think that, Michael. I think it was. I think I would have probably put more time and effort in the front side. Our budget for that maybe could have been, it personally could have been better to setting everything up, working with Planetate and then with Jenny to get everything set up and research the issue. But other than that, it's not been, that's not been a problem. It's more weather and equipment that's been our, nemesis, I guess. But we still, I think, have been very successful.
Good. Congrats.
Thanks.
Question here. Great presentation. Were you able to meet current design specifications for all PennDOT vehicles, or did you have to move the goalpost per se, given the net section reduction capacity issues with the T1 steel?
No, we didn't have to move. If it met it, then we drilled it. If it didn't meet it, we plated it. Like there was no playing games, right? It was quick decisions, because we had moved into this emergency, quote unquote emergency contract, but we didn't play around. I'm not going to do that, on a structure like this that's that critical. You just don't play around, right? Like if it doesn't get it, then we're out. Put a plate on it.
I actually had a follow-up similar to that. What was the downtime, I guess, or between a core? I mean, was the contractor ready to plate right after the core was drilled, or was there a downtime? And then I guess
you don't put a core and then drill it. Like it was either we took the picture, we took the analysis from the indication, did a calculation and said, oh, it's good to core it, it's going to be fine, or we're going to plate it. The only time there was downtime between a core and a plate was if we drilled the core and couldn't clear it, right? Like with a mag, right? Mag particle test. So that downtime sometimes was long because, again, you have to do the field work and the shop drawing and to get the approval of it and source the plate was sourced, but then they had to fabricate the plate and drill all the field shop drill all the holes and that kind of thing. So there was downtime between a core that failed and a plating, but almost all the other plating, that was only maybe 3 times. Everything else was, we knew it was a plate, that's it, it's a plate, right? From the get-go. So that's where we were at. So
great. Not necessarily a question, but anonymous user says, nice to see you. So I'm sure
nice
it's a friend.
Nice to see you too. I don't know who it is. Fantastic.
Sure, it's a friend. Next one here. Nice job. For the inaccessible welds, since they couldn't be fully tested, could you speak to future plans for accessing and inspecting those areas?
Well, this is another ringer, Bob Sahls. He's the HNTB lead for the inspection, and we've worked very closely with him. I'd like to say, and I'm grateful for it, for the course of the project to collaborate on, getting that safety line up and working on some other things. But we provided to HNTB for the inspection report our advice and collaborated on future inspection at those locations. There's, I think, 18 locations. I want to say 18 or 16 total. But because they need to you need to essentially do them via rope access. They're above the height of the max equipment that you can utilize, but they essentially have to kind of like utilize a little bit of like I don't know how to say it, like a piece of rigging, like, a strap or something to lift themselves on rope access up into that area and get a visual on that location. And if I was on camera, I'd be showing you like my hands, like there's like 5 or 6 different members framing into that. There's like a vertical and 2 diagonals and 2 top cords, and then maybe a lateral, and everything joins at like one weld spot in there. And so as a result, it's not even just like, it's a combination of things that are making them inaccessible, because first of all, you can't clean the paint. Second of all, you can't get in there to perform a test because you don't have clearance to do that. And then third is there's a conjunction of, I don't know if maybe intersection is a better word, of multiple welds at that location that wouldn't give us a clean answer on what weld we were looking at and what the results were. So as a result, we're basically saying, we can't give you a reliable answer from that perspective. And so a visual is just going to have to suffice that there's no problems there. What we did say, and we all know how we have to kind of like watch how we phrase things, we did say that the connection is very robust. So our concern about it being, a tension member or anything, there's a lot of redundancy there that would be, make you say, I'm probably not super worried about that being a problem in the long term. But to meet the spirit of the law, right, we're going to recommend that they be visually inspected every year, and that can be, or every other year, and that can be part of the biennial. So I hope that answers Bob's questions. But I think he was working on it anyway. So.
Well, it's just about time, and I don't think we have any more questions. But Jen, again, round of applause, everybody. I know you're sitting at your desk, but clap.
Thank you.
We all appreciate you coming on. This was a great project. You had a lot on your hands. I'm thoroughly impressed.
I couldn't have done this, and I would say I couldn't have done this without Josh Sadlock, who's, I don't think he's online because he's probably hanging from a bridge somewhere, but Josh really took this on, field operations lead, and he is amazing, and GFT is lucky to have him. So I would give him all the credit. And then construction side, Kevin Brown's been our lead there, and he's done a great job too. So I just need to give them kudos. But thank you. Thanks for having me. I knew I was worried I wouldn't have it. I would be short, but I guess I talk a lot. So.
No problem. And with it just to say, just from our organization and, all the different, companies that worked on this project and how we all work together on these, it's great that we can all share this experience and, collaborate together on future projects. And, you coming on and talking about this, it's nice to see.
Absolutely.
So, well, we do have a speaker gift for you. It's a Yeti coffee cup. We'll with our SEI logo and everything on. We'll be mailing that out to you. So again, we do appreciate that. And on the screen here is a QR code for the PDH, and I will also put a link in the Q&A form that you can get as well. So. Again, oh, look, Kylie already did it. Thank you, Kylie. So either in the QA, there's a link, or you can also scan the QR code there. So I'll leave it up for another minute and while everybody takes off. But again, Jen, thank you very much. Round of applause.
Thanks so much.
Everybody, hope to see everybody out at the social on the 14th. And we will be reaching out to everybody soon enough to talk about our October and November presentations. So be on the lookout. Thank you, everybody.
Have a great day.